Hey, AP Chem, we're going to continue our deep dive into kinetics. Honestly, not that deep of a dive. We're going to be kind of, wading into the shallow end a little bit more with kinetics. And today we're going to be talking about the integrated rate law. So the integrated rate law sounds vaguely terrifying because you're like, integrated is an integration with calculus. And technically, yes, it is derived from the integrated process of our rates that we take a look at, but you are not going to have to actually do any integration. So you can breathe a deep sigh of relief. At one point in my life, I used to be able to actually do that integration, but that has since left me. So we don't have to worry about that. We just need to look at the consequence of that integration, which will make life a little bit easier. So like I kind of had said before, the laws that we've talked about previously, the rate law that we just looked at, is technically called the differential rate law. So what it does is it expresses how the rate depends on the concentration. So it's how the rate is related to the concentration. It's called the differential rate law. And the integrated rate law, what it does is it takes that differential rate law and it integrates it with a time component. So what it does is it actually shows us how concentrations change as time progress once you know what your order is, or vice versa. So you could take a look at your concentrations and figure out the order, or you could see how that concentration changes with time if you know what order it is already. So what's going to look different in this situation is the data that you get from it. So a differential rate law is going to look different from an integrated rate law based on how much data you want to collect. So this is our previous unit, I guess if you want to call it, the setup of data for it. So you have multiple experiments using the method of initial rates to figure out our regular rate law. So from this situation, I would probably write rate equals and then the concentration of my different things. And here's a good example where I have 3 different reactants that I need to consider in here. Remember, again, coefficients are not important if we're looking at an overall balanced equation. This is a regular rate law, or what we call differential rate law. Integrated rate law data looks like this. What would happen is you would get a change in concentration or a bunch of concentration data and time. So what they did was they'd measure those values. If you remember from the beginning, we talked about that Alka-Seltzer lab. If I wanted to, I could actually take the data from that and take a look at those concentration values over time and figure out what the rate law is from that data. So it makes it so you only have to do one experiment, which is nice, but then there's a little more math involved with it, which is less nice. So it kind of depends. Now, with the rate law, we are only going to be kind of skimming the surface of what the AP, what I really think they're going to have you take a look at, and then we're going to dig in more to the math when we get into half-life, because half-life is related to our integrated rate law. So when we talk about our orders in integrated rate law, we typically only talk about one reactant affecting that. So like in that example that I talked to you about with the method of initial rates, you saw 3 different reactants. If I go back to this data, it's only 1. And that's partly because it is a graphic determination, or a graphical determination that we use to figure out the rate law. And so it is a lot easier if we're only looking at one reactant at a time. So the integrated rate law, what we have to do is we have to create a graph to figure out what type of order it is. And so we have our same orders, 0, first, and second. But what we do is we take a look at the graph, and what we're doing is we are looking for a straight line to show up. And depending on the criteria that I put on my Y and my X axis, that will let me know the type of order that it is. So here is a 0 order reaction. A 0 order reaction, we're going to focus on this graph here first, has a linear graph when I graph the concentration versus time. So if I start off my graph and I literally just take my molarity versus time, if it comes out as a perfectly straight line, I have a 0 order reaction, which we know means that whatever I do, it doesn't change the rate of the reaction. It's just always constant. So the concentration changes continuously, linearly, no matter what I do. Okay, so that's 0 order. Now, The zero order integrated rate law is this bad boy here at the top, and rearranged, it's this one in the white box. So what it is that my concentration of A at any point in time, so this is like A at like 50 minutes, whatever, is equal to A naught, which is my initial concentration, minus KT. Okay, K is our constant from before, and T is that time component. So the idea behind this is that if I want to figure out my concentration of A at any point in time, I'm going to take the negative value of my rate constant times the time and add it to my initial concentration, and it'll give me that value. I write it like this because this version looks a little bit more like the slope of a line. Y equals mx plus b. Time being our x component, and then, you know, that kind of stuff. This picture here is how they have it written on the AP exam. I think this sometimes is kind of helpful because of this reason alone. The K value, the rate constant in this case, is equal to the negative value of the slope. So if I would be given the slope, or I could calculate the slope of this value for this line here, if I took the negative value of that, that would be my rate constant. And if you think about units for zero order, units on that K value would be change in Y over change in X. So it would be concentration over time. And so it would be moles per liter per second or hour or whatever you have here. But the big thing you want to take away from this is in a zero order reaction, this graph is linear. We will dig into this math in our next section. We're just going to talk about mostly these graphs here. So when you graph the data, if you get a straight line and it's concentration versus time, it means your reaction is zero order. Now, first order, if you would graph concentration versus time, you would get kind of this drop, not exponential, but more like a logarithmic function. In the case of a first order reaction, though, if you took it and then took the natural log of that concentration data that was given to you and then graphed it and got a straight line versus time, that would be a first order reaction. So if you take the natural log of that big concentration data list and graph it versus time, you're going to get a straight line if it's first order. So it's natural log versus time. Now, what that translates to in terms of a Y equals mx plus b equation is that the natural log of A at any point in time is equal to negative KT plus your initial concentration's natural log. On the exam sheet, they rearrange it like this. So it's natural log at any point in time minus the natural log initial of your concentration is equal to negative KT. So just like before, we graph it, but instead of it being concentration versus time for zero order, it's natural log of concentration versus time for first order, and it's straight line. Okay, so it's this straight line that's important here. This is what it would look like if I would have concentration versus time. This is natural log versus time. Okay, now again, the slope is important on this graph because the negative slope value gives me the K value on this. Units on this are just 1 over whatever your time unit is. So that could be seconds, hours, whatever. Natural log of A, that molarity unit kind of disappears, and so you don't have to worry about it at all. Okay? Now, second order reactions. This is what a concentration of A versus time looks like for second order. If you take 1 over those concentration data molarity pieces, you get a line. So if I take 1 over concentration versus time, that gives me a linear graph, and it lets me know it's second order. Integrated rate law in slope form is 1 over A equals positive KT plus 1 over A initial. And then on the exam, they write it as 1 over the concentration at some point in time minus 1 over the concentration initial is equal to KT. So what's different about this one, you can kind of see our graph is going up in slope instead of like a downward slope. And so in this case, if you calculate the slope of this graph, it just is the K value. Units on this are going to be 1 over molar and then your time component for your K value. Okay? So this is probably not going to make a whole heap of sense. What we're going to be doing is I'm going to show you an FRQ. And like I said, at some point I might get into this math with you when we get into half-lives, but right now I just want you to understand the graphing relationships. So I'm going to show you an FRQ and show you what the heck I'm talking about. Okay, so this is an FRQ that was given on a past AP exam. You get 3 graphs here, and we'll go through this in detail, but when you see 3 graphs, you need to look at the graphs, see what is graphed where, and figure out what the order is. They do not necessarily put them in 1 or 0, 1, 2 order. Sometimes they do. Sometimes they mix them up to see if you're paying attention. So we're going to kind of, like I said, dig into this just a little bit with the DocCam, and then we will go from there. Now, one thing I wanted to show you before we get into this is the AP equation sheet. So if you look here, we've got 3 integrated rate laws written here, and they go in order. So this is 0, first, and second. And why I think this is useful to remember that it goes 0, 1, and 2 is what's in the rate law is what your graph is when it's linear. So for a 0 order reaction, it is concentration of A versus T. In a first order reaction, it's natural log of A versus T. And in a second order reaction, it is 1 over A versus T. So I think that's very helpful. The other reason I like to use this law a lot is because this negative or positive K value tells you how to deal with the slope. So if I have a negative K value here, if you think about this, that means that this slope is equal to my negative K, and this is my positive K. So just some kind of things to keep in mind as we're going along. Like I said, we will dig deep into this math when we talk about half-life right here, but we will get to that not today. Okay, so here is our reaction. Now, the crazy part about this is that this is a 4-point problem. So there's a ton of text, and I cut one of the problems out, but this is a lot of reading for 4 points. So just kind of take that in. So we've got this extremely complicated formula here. It tells us that blue food coloring can be oxidized by household bleach, which contains OCl-. So they're letting us know up here, and this is our dye, to form colorless products as represented by the equation above. The student uses a spectrophotometer set at 635 nanometers to study the absorbance of the food coloring over time during the bleaching process. In the study, bleach is present in large excess so that the concentration of OCl is essentially constant. So that's really important. When they do these and they figure out orders, they hold one of them at such a high concentration that we can really only observe the other one changing. So like I would change this concentration and keep it small and keep this one so big that it didn't look like anything changed. Student used data from the study to generate the graphs below. So if you look, we have absorbance versus time, natural log of absorbance, 1 over absorbance. So technically we aren't necessarily talking about concentration here, but we are looking at kind of roughly the same idea. Concentration, natural log of concentration, and then 1 over concentration. So again, it's not exactly the same, but it's not dissimilar. So it says, based on the graphs above, what is the order of the reaction with respect to the blue food coloring? So again, if we think about our graphs here, concentration versus time is 0 order. It's a 0th, if you want to call it. Natural log is first, and then 1 over A is second. Okay, so if we look at this, our data of natural log versus time is linear. So in this case, it is going to be first order. And in this case, it honestly doesn't even tell us to do anything else. It just says, what is the order of this? But if we wanted to explain it, we would say a graph of natural log of absorbance is linear, making it first order. And that's literally it, because they know if, like, that's just a common thing. Hey, if this is linear, it's going to be first order. If this guy were linear, it'd be second. If this guy were linear, it would be a 0th order. So that is just kind of what we accept. Okay, so B. It says the reaction is known to be first order with respect to bleach. Okay, so just, and again, this is maybe not super related to the problem, but it does tell us that now we know this is first order and this is first order. Okay. Reaction is known to be first order with respect to bleach. In a second experiment, a student prepares solutions of food coloring and bleach with concentrations that differ from those used in the first experiment. When solutions are combined, the student observes that the reaction mixture reaches an absorbance near zero too rapidly. In order to correct the problem, they propose the following 3 possible modifications: increasing temp, increasing concentration of the food coloring, and increasing the concentration of the bleach. Circle 1 that could correct the problem and explain the modification and how it increases the time for the reaction mixture to reach an absorbance near zero. So if you think about it, it's getting to absorbance of zero too fast. It means the reaction's happening too fast. So we need to think of something that's going to extend our reaction. If we look at our options here, increasing temperature, we know that that's going to make our speed go up. So that is no-go. Okay. If I increase the concentration of my food coloring, that is increasing a reactant. And we talked about how the OCl minus is in way excess, so that might be helpful. That's a positive one. And then increasing the concentration of the bleach, well, that's honestly so high already that that's not super useful. So we're going to talk about increasing the concentration of the food coloring. So then it says to explain how that would increase the time. So in this case, what we would say is we circled, remember to follow the directions, and explain how that would increase to zero or increase the time. So I would say if there is more reactant dye at the start, it will take longer for all of the dye to disappear. And then, which increases time. Okay, so hopefully that makes sense to you, is that if I have more reactant, and we talked about it, how increasing concentration of something increases the rate, which is true. So it does make it react faster, but if there's more stuff in there, it also takes longer for it to react in the first place. So that is our example for this. So we're going to kind of, like I said, get into a little bit more of the detail with these guys here when we talk about half-life, but for now, that is it. So if you have any questions, please make sure you get them cleared up. Otherwise, good luck.